Hello, everybody. My name is Adam Herrmann, and today I'm going to be doing a video presentation of a paper that I've submitted to the Spaceflight Mechanics meeting here in Austin, Texas. This work deals with a comparison of deep reinforcement learning algorithms for Earth-observing satellite scheduling. Before I begin, I'd like to thank my advisor, Dr. Hans-Peter Schaub, and I'd also like to thank the NASA Space Technology Graduate Research Opportunity for funding this work. So quick overview of the paper. I'm first going to discuss the motivation, then I'll dive into the multi-sensor Earth-observing satellite scheduling problem that we have formulated for this work. Then I'll discuss the algorithms that we use to solve the problem, namely MCTS train and proximal policy optimization. I'll then dive into the results and discuss a comparison between the two algorithms that we conducted, and end with conclusions and future work. Onto the motivation. So what is spacecraft planning and scheduling? Well, it's basically just computing the sequence of commands that a spacecraft must execute to fulfill high-level science and mission objectives. In the past, even currently, planning and scheduling is really a ground-based process. So pre-launch, you have some sort of mission design process, right? And for planning and scheduling purposes, really the important outputs here would be the trajectory, the science objectives, and even the parameters of the spacecraft, right? And all of these are kind of input into some activity planning software that schedules the sequence of tasks the spacecraft needs to perform. So here's an example here. Maybe you have to heat the instrument first, then point it at the target, and then take the image of the target. After activity planning, you sequence that plan into a low-level command sequence. This is then uplinked to the spacecraft for open-loop execution. So in our lab, we've looked at using reinforcement learning as a form of onboard planning and scheduling. There have been other techniques like iterative repair used at JPL that repair an a priori plan on orbit as necessary. But we're really interested in how we can transition to fully autonomous planning and scheduling, and we think that RL is a really good way to do that. So what exactly is reinforcement learning? Well, it's basically just learning how you can map situations to actions or states to actions to maximize a numerical reward signal. And what we're concerned with solving for is some policy pi that maps our states to our actions. And this policy can be represented in a tabular form, or most popularly with a neural network. And so this is kind of the objective in solving an RL problem. You're trying to solve for the policy pi that maximizes the expected value of the sum of all future reward while you follow that policy. So a couple great examples of reinforcement learning would be the AlphaZero algorithm, which achieved superhuman performance in the game of Go, or OpenAI 5's Dota 2 bot. And here are a couple graphics that demonstrate that. If you're solving an RL problem, though, you need to formulate it as a Markov decision process. So here's a diagram that kind of is an example of what an MDP might look like. So you have some decision-making agent in some state S0. It takes an action A0, transitions to a new state S1, and receives the numerical reward signal. And it selects that action following that policy pi. This process can repeat until the end of your planning horizon, or out to infinity, depending on your problem formulation. But here we look at fixed planning horizons. So how does this kind of compare to the ground-based planning and scheduling paradigm that I showed you earlier? Well, you'd really just replace the activity planning block with a training block. And then instead of a sequence of commands, you would be uplinking a policy. And then that policy would be executed in a closed loop fashion on board the spacecraft. So in our lab, we've done quite a bit of work on this, and some other labs are working on this as well. All the papers that I cite here are really for Earth observing planning and scheduling. There is a whole host of work out there that deals with GNC problems for small body exploration or other forms of deep space exploration, but I'm not going to touch on those today. So we've looked at using proximal policy optimization and kind of shields wrapped around the decision-making agents to kind of guarantee safe behavior, but also improve convergence during training. Myself personally, I focused a lot on using Monte Carlo tree search and supervised learning for EOS scheduling. And we found that we can compute optimal solutions, at least when we compare those solutions to what we would get from a genetic algorithm. And then, some other papers outside of the lab have looked at deep Q networks, the reinforce algorithm, I think A2C, et cetera, et cetera. But there are a couple problems, I think, with the past work. So every paper really only looks at one or two algorithms. So there's a real lack of comprehensive comparisons. And also each paper solves really a different flavor of the EOS scheduling problem. So we've come up with several research questions in this paper that we want to address. So first, which algorithm performs best? Based on our past work and what we've seen, our hypothesis is that MCTS train should perform the best since, just the way the algorithm works, we're kind of solving, we're exploring a search tree, trying to solve for an optimal solution that we then regress over. So seems like that should give us the best performance. We also want to see if policy gradient methods can produce smaller networks. And, in theory, they should be able to. So our hypothesis there is yes, it should be easier to learn the policy than it is to learn the state action value function. And then another question that we have is there a difference in total training time? Quite frankly, I don't know what the answer to that is. And that's kind of why we're doing this work. So we're now going to get into the problem statement. So we formulate a multi-sensor EOS scheduling problem where the goal is just to maximize the number of images taken with the correct sensor type. So that would be either sensor A or sensor B without violating our power and reaction wheel speed constraints. In this problem, we have a spacecraft in low Earth orbit operating over a 3-orbit planning horizon, which is quite short, but that's broken into 90 decision-making intervals. And to model the problem, we use a high-fidelity basilisk astrodynamic simulation wrapped within a gym environment. The gym environment's really nice because that provides a standard interface that all reinforcement learning libraries can effectively work with. So, we're not tied to one specific library. We can try out different algorithms from a bunch of libraries. So first I'll get into the MDP formulation. On the left-hand side here, you can see the state space. I won't go into everything in gruesome detail, but we have geometric information on the spacecraft position and velocity. We have information that deals with the attitude control system, the attitude states and rates. We have some information on our resources, like the norm of the reaction wheel speeds and the stored battery charge. And then we have some science-related information like target access indicators or the target sensor type. The action space is quite simple. We only have 4 discrete actions. We have a charging mode where the spacecraft points its solar panels at the sun to charge the battery. We have a desaturation mode where we use thrusters to remove momentum from the reaction wheels. And then we have 2 imaging modes that correspond with each of the sensors. And as I had stated on the previous slide, we're operating in 3-minute decision-making intervals. So each of these modes lasts for 3 minutes. And then here's the reward function. So the first component, we check if we fail. So if we exceed the reaction wheel speeds or we drain the battery, that gets -1 reward. Otherwise, we look at whether or not we were able to image a target. So if we image the target with the correct sensor, we return 1 divided by the total number of possible targets and some attitude normalization constant. So in theory, our max reward is 1 if we collect all the targets with perfect attitude using the correct sensor every time. And our minimum reward is -1. So we collect no targets and we fail. Now onto the methods. So the first method that we use is MCTS train. Really, this is kind of a value-based method. So we use Monte Carlo tree search to generate estimates of the state action value function, shown here, Q hat S of A. We'll generate typically around 45,000 of these data points. And then these are then regressed over using a variety of neural networks with different hyperparameters. And then, so each of those neural networks is kind of its own approximation of the state action value function. And then those approximations are then benchmarked in the environment. And we use this policy here, pi of S equals the argmax of the state action value function Q sub theta. The other method that we're using is proximal policy optimization. So it's kind of a mix between a policy gradient method and, well, and it's also an actor critic method. So here's the loss function here. We have policy loss, which is this L clip. We have value function loss, and then I think this component here is entropy. Basically, proximal policy optimization. So for however many iterations, we initialize, or rather, n actors, and then each of those actors goes out and gets experience in the environment with the current policy. We compute the advantage estimates based on that experience in the environment, and then we optimize our loss function for k epochs and some batch size. And then we just repeat that process. So the agents are constantly going out in the environment, getting information, we're regressing over that using the networks. Okay, so onto the results. So the first algorithm that I'll talk about is MCTS train. And kind of the first step when you're working with MCTS is to figure out how much you need to explore the problem space and how much kind of computation you need to throw at the problem. And that's controlled with two different hyperparameters. So we have an exploration constant, which is shown right here. We go from about 0.1 all the way up to 4. You'll notice that it's somewhat around the order of magnitude of our reward function. And then our number of simulations per step goes all the way from 5 to 80. So at every step through the environment, MCTS will either run 5 or 80 simulations to select the next best action. On the left-hand side here, we use a more conservative rollout policy. So we look at the safety states and we say, if any of the safety states are at about half of their limit, we take the safe action. Otherwise, we do science. On the right-hand side, if our wheel speeds are at about 80%, we'll take a safe action. If our battery charge is at, I think, 20% depth of discharge, we'll take a safe action. So the rollout policy on the right is a lot more aggressive. And you can kind of see that we get between like a 10 and 20% performance increase, depending on the hyperparameter combination. So the more aggressive rollout policy is what we use for training because we're getting better reward, and therefore we think we should get better policies. So we select this hyperparameter combination here, which is somewhere around 0.65 average reward, and that's at 20 simulations per step with an exploration constant of 4. You want to keep the number of simulations per step at a minimum because the fewer of those, the faster it takes to generate your training data. The next step is the function approximation for MCTS. So we roughly solve 1,000 initial conditions with MCTS, and then we apply supervised learning over that data set. And so here are some of the details for the hyperparameter search we performed. So we looked at 1, 2, and 4 hidden layers, and then 10, 20, 40, 80, and 160 nodes per hidden layer. And we also add dropout between the layers. And so that's really just the probability that a node's going to be dropped during training. And that, in theory, should help with overfitting. So here is a table of the performance for each of those networks. Anything in red is an average reward of less than 0.3. Anything in yellow is between 0.3 and 0.6. And green is above 0.6, right? So we would consider those to be good performing networks. And you can see that usually dropout helps us. As the networks get larger, performance increases. But by no means, can we guarantee kind of good performance for these larger networks, right? Most of the time, we're actually struggling to match the reward found by MCTS in the data generation step. And this honestly is kind of surprising because in past work, we've been able to match that policy kind of no problem. And we haven't required massive networks to do so. So we're kind of actively figuring out why that's the case here. And I'll talk in a few slides as to why we think that might be. So yeah, learned policies struggle to match the performance of MCTS. The next algorithm is proximal policy optimization. So we did several hyperparameter searches here. The first one was just a general network size search. So this is basically the exact same search that you just saw on the last slide, but for PPO. And here are the results. So we're only looking at the networks without dropout. And you can see that, as the networks get larger, there is a very clear correlation with reward. So we get up to about 0.75 average reward for our largest network. That's really good. But this requires anywhere from 1,000 to 10,000. I mean, I think actually like 80,000 trainable parameters. Those are pretty large networks, and in theory, policy gradient methods or policy-based RL methods should be able to produce smaller networks. So, can we go smaller? So, I'd like to thank John Martin in our lab for giving me some guidance on how to perform this hyperparameter search. He's kind of our neural network expert. And what we did was we kind of varied the batch sizes and the number of training epochs per iteration of PPO. So we looked at batch sizes about, I think, 1/2 and 1/4 of what we had before, and then epochs that 5 and 10 times the original amount. And this is what we get, right? So here we just look at one network. We look at a network that is 4 hidden layers deep and 20 nodes wide. We can see that we get actually really good performance almost across all of these hyperparameters, which is great, right? So this was the original right here. That maps to this right here. And you can see that with a 1/4 of the batch size, but maybe 10 times more training epochs, we're able to get in that green zone. So that's really good. But now we want to know what happens when we reapply what we've just found here to the original experiment. Does this apply to the larger networks? And no, not necessarily, right? So as the networks get larger, our performance starts to decrease a little bit. We're not in the red, but we do get yellow. But that's really for kind of the largest networks. Most of the networks still perform extremely well. So really this suggests that larger networks might require a larger batch size and or fewer epochs. We don't know yet. We have to perform that experiment, but really that doesn't matter too much. What's important here actually is that we were able to train very small networks, right? So 1 hidden layer and 10 nodes. That's 183 trainable parameters to achieve almost 0.7 average reward. So for onboard execution, that's excellent. Okay, so in conclusion, we'll kind of revisit those original research questions. Number 1, which algorithms perform best? So far, we've shown that PPO produces the best performing networks at about 0.75 average reward. MCTS and the subsequent supervised learning definitely had a much more difficult time producing optimal performance. We're not quite sure why, but one theory, at least, is that for this problem, we have 4 to the 90 possible trajectories through the environment. In past work, we've only had 4 to the 45. So the complexity of the problem might just be blowing up to such a degree that MCTS is no longer viable. But we need to look into that in future work to determine if that's really what's going on here, or if there's something wrong with the rollout policy or something more fundamental. The second question we had was, can policy gradient methods produce smaller networks? The answer to that is yes, at least so far we think so. Again, it's a little bit hard to tell when we think MCTS might not be performing as well as it could be. And we really should compare to other value-based methods like deep Q networks to figure out if that's really true. And then lastly, is there a difference in total training time? So it really depends. PPO can produce a single network in only about 3 hours. But to do a large hyperparameter search, both algorithms take 1 to 2 days to complete that search. For MCTS, this is largely due to the time it takes to generate the training data, right? So that's really what takes most of your 1 to 2 days. When you have all the training data and you have a good GPU, it only takes a couple hours to train, 30 or so networks. So in future work, we want to look at different environments. So this environment was the multi-sensor env. I also have a kind of like an agile Earth observing environment, as well as a small body environment, both with kind of increasing problem complexity in some areas, but maybe less computational or problem complexity in other areas. So I'd like to compare to those as well. And then I'd like to look at some additional algorithms. So both shielded and unshielded PPO. Everything I showed today was unshielded PPO. Also deep Q networks, maybe A2C, and the reinforced algorithm. With that, that's the end of the presentation. If you have any questions, feel free to send me an email at adam.herrmann@colorado.edu. And I appreciate you listening to this video presentation.